Sorting data points into isolated groups is easy. Finding the mathematical best way to draw the line between them is a much harder geometric problem. Solving that problem is the core objective of a support vector machine, taking a dataset and discovering the optimal separating boundary. In this two-dimensional space, there are an infinite number of valid lines that separate the blue circles from the pink ones. But an SVM rejects arbitrary boundaries. It seeks the single optimized hyperplane, line L2, maximizing the empty space between classes. This diagram shows exactly how that optimized gap operates. The empty space bounded by the parallel lines is the margin. These lines are physically anchored by specific data points, the green star and purple circle. These are the support vectors. They are the only points the algorithm evaluates. Every other interior data point could be entirely erased, and the boundary wouldn't shift by a single millimeter. This selective blindness to non-essential data makes the SVM a memory-efficient model, as its decision boundary is anchored by only a handful of specific coordinates. Of course, that perfect geometric separation is rare. Real-world datasets are messy, overlapping, and filled with outliers. On the left, a hard-margin SVM demands absolute perfection, with zero misclassifications. Notice how the boundary skews its trajectory to avoid a single red outlier. The fatal flaw here is severe overfitting. The model memorizes the noise rather than learning the actual underlying pattern. Shifting to the soft margin on the right, the model intentionally allows a few points to violate the constraint, yielding a much wider, stable boundary. To make an SVM functional outside of a sterile lab environment, engineers willingly trade perfect training accuracy for a robust model capable of generalizing to new, unseen data. Data scientists control this strictness using a mathematical dial called the C parameter, a process known as regularization. The right graph displays a C value of 100. This large C applies a heavy penalty for errors, forcing a narrow margin that risks overfitting. Dialing C down to 1 on the left accepts misclassifications, but buys a broader margin to absorb outliers. Adjusting this parameter allows engineers to physically balance the bias-variance trade-off. But even with the perfect C value, the algorithm is still trying to draw a straight, flat line. That straight line is completely useless when a dataset possesses nonlinear geometry. You cannot draw a flat line through a circle of points. The elegant geometric solution is to apply a nonlinear transformation, physically bending the two-dimensional space into a higher dimension. This visualization shows the result. We take the entangled 2D points on the left and lift them into the 3D bell-shaped curve on the right. Classes that were completely mixed on a flat plane can suddenly be cleanly separated by a flat slice. There is a severe operational catch. Calculating entirely new 3D or 4D coordinates for millions of data points requires an immense amount of processing power, often enough to crash standard computer memory. Data scientists need the spatial separation provided by higher dimensions, but they cannot afford the computational cost of getting there. High-dimensional geometry becomes computationally viable through a mechanism called the kernel trick. To find the optimal margin, the SVM algorithm does not actually need to know the exact physical coordinates of the data points in the higher dimension. It only requires the inner product, a scalar value representing the similarity or distance between those transformed points. A kernel function is an equation that computes this high-dimensional inner product directly, while the data remains physically plotted in its original low-dimensional space. The kernel trick gives the SVM the ability to act as if it is slicing through infinite dimensions, without consuming the memory required to actually render them. This grid displays the menu of kernel functions a data scientist can apply, from linear boundaries to polynomials and sigmoids. Look closely at the radial basis function graph. RBF is the industry standard default for nonlinear data, drawing tight circular boundaries directly around distinct clusters. It is highly effective because it maps data into a space of conceptually infinite dimensions. To tune an RBF kernel, engineers adjust the gamma parameter. Gamma dictates the radius of influence of a single support vector. These two charts illustrate the mechanism. With a higher gamma on the left, data points only evaluate their immediate neighbors, resulting in a tighter, more restrictive boundary. A smaller gamma on the right expands their reach, smoothing the boundary over a larger area. In a nonlinear model, the engineer uses the C parameter to control the strictness of the margin and the gamma parameter to physically sculpt the shape of the boundary itself. Deploying an SVM effectively requires addressing a specific operational constraint, the scale of the input data. Because the algorithm inherently relies on measuring physical geometry and distances, like margins and dot products, it is hypersensitive to the scale of the input data. The mandatory rule for deployment is that all features must be mathematically scaled before training begins. The before scaling chart shows misaligned distributions where large raw numbers dominate geometry, rendering parameters meaningless. Conversely, the after standard scalar graph forces features to the exact same magnitude, aligning data peaks on a centralized axis to accurately measure distance. An SVM is a highly precise engine for finding order in complex data. It works by balancing strict geometry, leveraging the high-dimensional math of the kernel trick, and operating inside a properly scaled mathematical universe.